Welcome to Pre-Calculus Trig, section 1.4 on the unit circle. The unit circle is a circle with a radius of 1 that is centered at the origin. So the unit means 1. That's why we call it the unit circle, because the radius is 1. Now this equation here, the equation of a circle, comes from the standard form of the equation of a circle, which looks like this. So if h is 0, the x-coordinate of the center, and k is 0, the y-coordinate of the center, and r is 1, then we end up with x squared plus y squared is equal to 1. So this is the equation of the unit circle. So any point on the circle itself has a coordinate pair xy, where x squared plus y squared equals 1, meaning x and y satisfy the equation of this circle. So if we take any point xy on the circle and we draw a radius from the origin to that point, we've created the terminal side of the angle theta in standard position. We learned about angles in standard position in our last unit, where this is the initial side and this is the terminal side of the angle theta. So the positive rotation would be in this direction and a negative rotation would be in this direction. So we've already established that we could hit any angle in this domain here, negative infinity to positive infinity, if we take into account coterminal angles. So what that means, to review from last unit, is that if you have an initial side here and a terminal side here, let's say this is your theta at maybe 60 degrees. You could also land on that same terminal side if you added a full rotation, and you could do that infinitely many times, and that angle will just keep growing and growing and growing more positive to become a greater positive number, so that you can establish in your mind how you could approach infinity that way. Now, if you rotate it in the negative direction from this terminal side here, you would be subtracting 360 degrees over and over and over infinitely many times. And you could see how you could approach negative infinity by continuing to subtract 360 degrees over and over. So this establishes how we can have a domain over all real numbers for the angle theta. So our goal here with the unit circle is to find a simplified way to express sine and cosine when we want to talk about them as functions with the domain negative infinity to positive infinity and start graphing them on the coordinate system. So we want to write x, sine and cosine in terms of this point x and y, in terms of x and y. So if we look at this triangle right here, this would be your opposite side, this is your adjacent side, and this is your hypotenuse. So if I wanted to say sine of theta, which is opposite over hypotenuse, in this diagram, it's y over 1. And then the cosine of theta is adjacent over hypotenuse, so that would be x over 1. So we can see that the sine can simply be taken as the y-coordinate, and the cosine, the x-coordinate in my point. So this point here is really the cosine of theta, the sine of theta. That's another way of writing the point xy. And this is why the unit circle is useful, because we, in our other equations in the last unit, and we had any r, then you would end up with an r in the bottom, and it wouldn't be so simple to say that the point xy is just the point cosine of theta, sine of theta. So this simplifies our writing of the cosine of theta and the sine theta by restricting that hypotenuse to 1. And one more point to make here is if you were writing the tangent of theta, which is a quotient, so the tangent of theta is equal to the opposite over the hypotenuse over the adjacent. So in our triangle there, we'd have y over x. So you see the radius doesn't play into the calculation of the tangent. All right, so this helps us out a lot with simplifying how we're going to write cosine and sine. So looking at this slide here, when your radius is equal to 1, the 6 trig functions simplify to the following. So the r is taken out of any of these here equations. So the sine of theta is y, the cosine of theta is x, the tan is y over x, and then these would be your reciprocal functions. So every point on the unit circle is an xy coordinate pair, which is represented by the cosine of theta, comma, the sine theta, for any angle theta on the unit circle. So this diagram here is your standard depiction of the unit circle. Now it looks a little busy, but you get used to it after a while. Now this you can see in pretty much any trig book or all over the internet. If you're searching for a unit circle, this is generally how it's going to look. So it's broken into, let's look at these bullet points over here. The 45, 45, 90, and 30, 60, 90 special right triangles are shown on the standard diagram of the unit circle. Right? Second bullet says the xy coordinate pairs show the lengths of the legs of these special right triangles. All right, so let's refine this first bullet a little here, and I illustrate how it's broken up. So let's talk about the 30-degree angles first. So starting at 0, 30, 60, 90, and then you can see I'm marching around by 30 degrees, 120, 150, 180, 210, 240, 270, 300, 330, and then back to 360 degrees. All right, so I'm broken up there into 6 30-degree segments on the top and 6 on the bottom. So 12 30-degree angles over a total of 360 degrees. Now let's look at the 45-degree angle lines. So starting at 0 degrees, I'm going to go every 45 degrees now. You can see there's 2 45s for every 90-degree quadrant. So you can break the entire triangle into 45-degree segments as well. So these are our special right triangles within the 360 degrees. Now let's look at how we get the coordinate pairs from these special right triangles. So let's start with the 30-degree triangle that looks like this. I'm going to drop a perpendicular down right here, where this will be my x dimension and this will be my y dimension, and then the radius is 1. So using Pythagorean theorem like we did in the last unit, let's put the angle measurement in here. This is 30, and of course this would have to be 60. We can establish that the short leg, the y dimension, is 1/2, which is half of the length of the hypotenuse, and the x dimension is the longer leg of the 30, 60, 90 right triangle, which is √3 times the short leg. So that would be √3 times 1/2, which is √3 over 2. So these numbers should look familiar. So that means your x coordinate is √3 over 2, and your y coordinate is 1/2. And you can see this triangle reflected across the y-axis right here. Now your x-coordinate becomes negative, and your y-coordinate is still positive. And then you can reflect that triangle across the x-axis, and you'll have its equivalent with different signs in the third quadrant, where the x-coordinate is negative and the y-coordinate is negative. All right, and then I can reflect this triangle here across the x-axis and get this triangle in the fourth quadrant where your x-coordinate is positive and your y-coordinate is negative. All right, so that's how we get those coordinates from the Pythagorean theorem using a 30, 60, 90 triangle with the radius of 1. So now, let's flip that original 30, 60, 90 degree triangle up in this orientation so we can see how we get the coordinates of this right here, this 60 degree angle, where 60 degrees I mean from here to here. So if that's 60 degrees, that means this is 30 degrees, and here this is 60 degrees here. So this is still a 30, 60, 90 triangle, which means the short leg is 1/2 of the hypotenuse. Hypotenuse is still 1, and the long leg is still √3/2. So now you can see that the x dimension is 1/2, and the y dimension is √3/2. So these two right here are just flipped in the x and y direction. Now, if we go around the unit circle, we can develop that there are 3 other triangles just like this in the other 3 quadrants. So there would be this one here. All right, and then reflecting, so that's reflected across the y-axis, and this one here reflected across the x-axis, and then reflecting this one across the y-axis. I'll also get this one here, and if you look at the coordinates, you can see that they only differ in the signs relative to which quadrant they're in. In the same way with the other 30, 60, 90 triangle in the other orientation. Okay? So you can see that pattern there. All right, now let's take a look at the 45 degree triangles. Now let's talk about the 45 degree triangles. So let's look at this one first, in the first quadrant. So this is 45, 45, 90. So with the radius of 1, using Pythagorean theorem and rationalizing the denominator, we can find that these 2 legs, which are congruent, have the dimension √2/2. So that would be positive x and positive y in the first quadrant. All right, so now I can see that I've got this triangle. If I reflect that original one across the y-axis, and then I've got this triangle equivalent. If I reflect this second one across the x-axis, and then I've got this one. If I reflect the original triangle in the first quadrant across the x-axis, I have this equivalent triangle. So you can see that those 4 triangles have the same x, y dimensions. The only difference would be in the first quadrant, x and y are positive. In the second quadrant, x is negative, y is positive. In the third quadrant, both x and y are negative. And then in the fourth quadrant, x is positive and y is negative. So the final thing to talk about then is the quadrantal angles, which some people call them. These are the 0, 1 coordinate pairs on the axes themselves. So the way to think about this 0 degree angle here, so that we can understand how this 1 and 0 come about, is to think about a really skinny triangle. Here's your origin. Here's your hypotenuse of 1 on the unit circle. And your theta is approaching 0. Of course, if it actually was 0, you would degenerate into a straight line. All right, so if we still think about this as a triangle, get that this angle here approaches 0, then we could see that the cosine, which is the cosine of theta, which is the adjacent side. So here's your adjacent side over your hypotenuse. You can see that the adjacent side over your hypotenuse is going to approach 1, because if you close up this triangle right here, this side eventually lies on top of this side over here, and they would both be of the same length 1. So that's why this definition of cosine of theta being x and sine of theta being y still holds for these quadrantal angles here, if we think about 1 as being the limit of the size of the angle of the cosine of the angle theta. So as theta approaches 0, this angle basically collapses where your adjacent over your hypotenuse approaches 1. Okay, so that's how you can rationalize that in terms of triangles. Now, as far as sine goes, sine of theta is defined as your opposite side over your hypotenuse. So, whoops, this is my opposite side in my little small 0-degree triangle over here. So my opposite side is going to approach 0, and my hypotenuse is going to be 1. So you can see how the sine is going to approach 0 as this angle theta approaches 0. So that's how you can understand this 1, 0 coordinate pair in terms of triangles. But most of the time we think about that 1, 0 pair is just the coordinates of this dot right here, 1 in the x, 0 in the y. And that same rationalization you could use for this angle over here, where you get a negative in the 1 and a 0 in the y, because you can see that the same thing would occur. The opposite side of a very skinny triangle over here would give you a sine of 0, and the same dimension for this long side. This long side is going to approach the length of the hypotenuse, which would give you this negative 1 over here, where we have a negative sign on the side length over here. But more often than not, we just think about this as the coordinates of that point. Negative 1, 0, the coordinates of that point, in keeping with the definition of sine and cosine on the unit circle. And you can use that same type of rationalization for trying to understand how these coordinates here and here could actually have something to do with triangles. So if you draw that little skinny 0-degree triangle up in this orientation here, all that does is flip these coordinate pairs, the understanding of what they mean. So this long side approaches the length of the hypotenuse, which is 1, and that ends up being in your y orientation with your triangle flipped on its side like that. So that's your sine approaching 1 this time. All right, and this little skinny side here being your adjacent side in this orientation is going to give you your cosine being 0 if you take this side over here, this really, really small 0, almost 0 side over the hypotenuse is approaching 0, so it would give you this cosine value of 0 in this orientation here. So for those of you who are wondering, how can you even think about these quadrantal angles as having anything to do with triangles? You can think about them as basically degenerate triangles. So that leaves us with the bottom line here, that the domain for the cosine of theta is anywhere between -1 and 1, and the domain for the sine is anywhere between -1 and 1. So you will never find a value of cosine or sine outside of these limits. So that wraps up our discussion of how the unit circle is arrived at. And now in the second part of this lecture, we're going to do some example problems using the unit circle to solve some trig problems without using the calculator.